Yeah, so my name is Geest from VIP. I'll be presenting some work done as part of Neuroscience Gateway. So basically the topic is dynamic meta scheduling in Galaxy with something we call the TPV Broker for smarter workload distribution. So what Neuroscience Gateway, more or less the tagline of it is leveraging the European compute infrastructure for data-intensive research. So these are the institutes involved. So basically, to leverage this distributed infrastructure, compute infrastructure, within all the organizations involved in the project, we want to do that by employing Pulsar. So Pulsar is a Python application that sits on top of your scheduler or infrastructure. That could be a Slurm cluster. And so basically that converts all, or makes all those infrastructures available to a specific Galaxy as Pulsar nodes. And this is then coined the Pulsar network. So yeah, this is again, kind of repeating the Pulsar network within the project there. I think we're at 10, or probably at a bit more, because we have some like the Czech people involved have more than one, I think. So now, how do we efficiently schedule our jobs between all these different Pulsar endpoints? And that's basically what we wanted to work on, how to do this efficiently. So by default, Galaxy has something called TPV, or Total Perspective Vortex, which is basically a Python slash, it employs YAML, but it's kind of a piece of software to connect all different tools with different requirements, plus the users invoking the tools with their specific requirements to specific destinations or compute destinations. And it tries to do this in using YAML, basically. So it kind of puts together requirements of the three things at the top. So tool-specific requirements, users, and Galaxy roles. So these are groups of users. Puts all these requirements together and evaluates that against the destinations. So you could think about CPU and memory requirements, and then trying to match that against the destination, that what the destination has configured as basically the maximum allowed capacity. So here's an example. So the tool will have these kind of requirements on the left. And so basically TPV tries to match that basically in a static way. And here, you can see both of these destinations can in theory run this job. However, the destination with GPUs could run this job, but this is maybe not efficient if you have GPUs there. But so this is it kind of just orders the destinations, and it will try to fit it into one of the available ones without necessarily ranking them or saying one is better than the other. So another thing you can do in TPV is tagging. So these are scheduling tags. So for example, in this example, this tool has a offline tag, meaning that if a destination is marked as offline, then obviously the job shouldn't go there, and it tries to do this matching as well. So another last thing that TPV also kind of can do is to have it has like an insertion point or an entry point for kind of custom Python code for kind of providing a rank of all the possible destinations. And this is actually our entry point as well for what we developed. So basically the current limitations of TPV by default is that it doesn't consider the load on all these different pulsar endpoints. It doesn't account for idling jobs, and it also doesn't account for basically the distance from the Galaxy server to the destination. So our goal was to integrate real-time metrics into this scheduling. So we introduced the TPV Broker, and we also published a paper on this. So basically, we improve TPV try to enhance it by providing all these different metrics about the destinations, checking the geolocation, and we kind of look at what the current queue is at these destinations. And we put this, we covered this with the TPV Broker, which consists of a few different components. So a producer-consumer model, which is, it's RabbitMQ in this case, which gathers all of these metrics and puts them into one location. We have a Python application that actually does the ranking of the destinations, and we have the Galaxy Job Radar for the visualization of where jobs are being sent to from the Galaxy instance. And this is kind of the workflow. So when let's see, when like a job comes in, it'll first try to match it with through TPV, and TPV sends sends an API request to TPV Broker. TPV Broker so collects all these metrics into an InfluxDB, and then the TPV Broker does the calculation of all the metrics coming from the pulsars, and provides then a ranking of the best destinations back to TPV. So the part of this is the matchmaking algorithm, so matching the job to a destination. So we have to filter out destinations that cannot meet the job currently. We calculate the distance, and we calculate a matching score based on the queue and the current amount of running jobs on the destinations. And we finally sort it based on this score plus the proximity of the destination. This is the formula of this matching score. So it considers the median queue time and the queue size across a small window. And it also considers the median runtime and the amount of running jobs in the same window. So it's accounting for queue size and current workload of the destination. So puts these things together, just adds them up, and then gives more or less a ranking based on that. So also in this context, the Galaxy Job Radar was developed. So it's a visualization tool, and it's kind of supposed to show real-time job distribution, which admins could use to detect maybe faulty destinations. That's kind of what it looks like. There's been some improvements on this, so I should probably get an updated slide for this. And yeah, so basically summarizing kind of the benefits. So it's real-time resource tracking. So it's scalable. You can introduce more endpoints. And we also made it so that the broker kind of detects offline destinations, but it could also direct jobs to underutilized destinations as well. Some future work. So we still want to enhance the algorithm that we've developed for this. We also want to at some point account for carbon usage of the specific destination. So maybe preferring destinations that use green energy. And we also want to enable data that's already cached at specific closer destinations to not have to be re-uploaded. So that the jobs can run there if the data is already available there. There are some machine learning things we could think of with the historical scheduling data. Want to improve the job radar as well with additional metrics. Finally, I want to thank the people we worked with on this project. I should also thank the people from CESNet that worked on the Galaxy Job Radar. That's it. Thank you.
Thank you very much. Question? Yeah. Hey there. Thanks. One question that has been a pain point for many of the people that I've helped with their compute, distinguishing system failure from user triggered failure. So when is it that the system failed versus the user did a mistake? And since you mentioned fault tolerance, is there anything built into the system to allow that? For instance, if it detects that one target failed, that it automatically submits to a different one or anything like that?
So for job resubmission, I think other people have been working on this. I think, for example, Bert has been working on this, and I think there is some things already in place for that. In Galaxy. This is not necessarily part of what we developed. It's more to detect whether the scheduler itself is doing what it's supposed to do. If something is broken in the scheduler itself.
So, I mean, we ran into a similar problem on our org, and we used a very pragmatic solution. If the job time is short and failed, we have a post script that marks the node as offline. And then, you can look at your cluster and see how many nodes are online, so that sort of avoids the black hole problem of like everything fails really quickly on the node, so all the jobs go to that failing node, right?
And just one more question regarding the routing part and the whole assessment of what is available and not. Did you take any inspiration from any other existing projects that have similar challenges? Tor came to mind, for instance.
So in terms of like the algorithm, we were working. So basically, it's Abdul Rahman from the Norwegian partner did a lot of work in like these scheduling algorithms specifically, and falsifying all these inputs as well. I would have to look at the Tor project, but I guess I can't give like a good answer on that.
So we kind of trusted a learner because he did his PhD exactly in that. So he has done the gap analysis and all these formulas, and he drove this project from that side, from the scientific side. And he wrote his PhD thesis about that. So there's a huge thing that we could all study.
No more questions? Thank you, Paul.